Hi, in this session we'll study about more applications of digraphs. Okay, in our combinatorics course we have studied about relations. Okay, in particular we are more focused on binary relations. So what is a binary relation? Okay, binary relation is actually a subset of, suppose we have a set A. Okay, so binary relation is actually a subset of A cross A. Okay, so we call by, so there are, we studied many binary relations. For example, we studied the divisibility relation, we studied the greater than equal to relation, there was a parallel relation. So in a set A, suppose if two elements are related by some binary relation, we will represent it by the symbol A related to B. Okay, so we studied that A was less than or equal to B, so we have studied some properties of the relation. Similarly, we studied about A is parallel to B. So these type of relations we have studied in our last course. Okay, so we will now study how to represent such binary relations using directed graphs. Okay, so suppose you have a relation R, which is a subset of A cross A, and suppose you are representing elements A and B like this. If R, they are related, we will represent it by A and B. Now let us see how to represent such relations using digraphs. It's very simple. What you are going to do is that we will actually represent the elements of this A by vertices. Okay, suppose your elements of this set A. So your elements of A are, for example, 1, 2, 3, 4. Suppose there are only 5 elements, and then we will represent them by vertices. Now if there is a relation from 1 to 2, suppose if 1 and 2 are related like this, 1 related to 2, okay, we will draw a directed edge from 1 to 2 like this. So here the order is important. 1 to 2 related does not mean 2 is related to 1. So if 1 is related to B, I'll just draw an edge from 1 to 2. Okay, and if 2 is related to 1, again I'll draw another edge which starts from 2 and ends at 1. Okay, this is how you are going to represent binary relations. And similarly, if 3 and 5 are related, I'll draw an edge from 3 to 5. Okay, if 3 is related to 5, if 3 is related to 5, I'll draw an edge from 3 to 5. And if 4 and 3 are related, and if 4 is related to 3, I'll then draw an edge from 4 to 3. So this is how I will be representing binary relations. Suppose 3 is related to 3 itself. Suppose there is 3 is related to 3. So if you are using less than or equal to relation, you always know that A is always less than or equal to A. So if 3 is related to 3, I'll just draw a loop. Okay, so this will be a direct self loop I'll be drawing there. Okay, so this is how we'll be representing binary relations. So you will be representing the elements of the set as vertices. Then you will draw directed edges from A to B if A is related to B. So this is how we will be representing binary relations. Okay, it's a very simple concept. So here is an example of a binary relation which I have drawn here. We can see it here. So here A was the set 1, 2, 3, 4, 5. So here 1 was related to 1. So we will draw a self loop at 1. And similarly 1 is related to 2. So we will draw an edge from 1 to 2. Okay, and similarly you can see that 4 is related to 5. So the edge was related from drawn from 4 to 5. And similarly 5 is related to 4. So an edge was drawn from 5 to 4. So like that you can try to draw this basically this diagram corresponding to this binary relation. Okay, so this is how we will represent diagrams using binary relations. And now we will see some special cases of binary relations which we have already studied, called reflexive, symmetric, transitive, equivalence. So let us see the diagrams of them also. Okay, so what is a reflexive relation? You always know that reflexive relation, for every element A, it is always related to that element itself. Okay, so that means A is always related to A for all A element of A. That is the concept here. For example, less than or equal to is a reflexive relation because always A is less than or equal to A, but less than is not a reflexive relation because A is not less than or equal less than A. Okay, so you know what do you mean by reflexive relation. Every element should be related to itself. Okay, so when you draw the diagram of such a reflexive relation, what will happen? Every element will be related to itself. That means every element will have a self loop like this. Every vertex will have a self loop like this. Is it clear? So when you represent the diagram of a reflexive relation, the property is that every vertex would have a self loop. Okay, because that every vertex is related to that itself. So you will have to draw a self loop there. So in the diagram of a reflexive relation can be recognized by the fact by looking that every vertex should have a self loop. Okay, now if every vertex do not have, so suppose none of the vertex have a self loop. So if suppose none of the vertices have a self loop. Okay, what does that mean? That means none of the elements are related to itself. Okay, such a relation is called a irreflexive relation, and we have studied more in the previous courses. Okay, so if none of the vertices are related to itself, it is called a reflexive relation. Okay, if all the vertices are related to itself, it will be called a reflexive relation. And in a reflexive relation, it will have the corresponding diagram will have self loops at all the vertices. Okay, and in an irreflexive relation, this is just for information, none of the vertices would have self loops. Okay, so moving forward, What is a symmetric relation? That also you know. Okay, so if A is related to B, you know that B should be related to A. Okay, if A is related to B, you should know that B is also related to A. Okay, that is what you mean by symmetric relation. Okay, for example, equality is a symmetric relation because if A is equal to B, definitely B will be equal to A. Parallel, if the lines are parallel, if L1 is parallel to L2, we know that L2 is also parallel to L. So parallel to is a what do you say? It is a symmetric relation. Okay, so using and similarly, so these are the concept of symmetric relation. And what will be the diagram of a symmetric relation? So if you draw an edge from A to B, you should also have an edge from B to A. Okay, so this is the example of a, so for every edge from A to B, you should have a edge in the reverse direction also. So such type of graphs already we know by a name in the last session. What was they called? They were called symmetric graphs. Okay, so in a symmetric graph, for every edge from A to B, from vertex V1 to V2, we will have an edge from V2 to V1 also. Okay, so that is, so symmetric graphs are actually the representation of symmetric relation. Okay, so if there is an edge from the vertex A to B, you should also have an edge from the vertex B to A. Okay, so this is an example of a symmetric relation. Okay, now if you know that a graph is a symmetric relation, you can also represent, in some textbooks also represent symmetric relations by undirected graphs, because in an undirected, so suppose in this graph itself, suppose I am representing it is like this, that is x1, x2, x3, x4. Okay, so this is an undirected graph, so that means that I can go from x1 to x2 and also I can come from x2 to x1. So sometimes in some textbooks undirected graphs are also used to represent symmetric graphs. Okay, that is basically to reduce the clutter. If you have so many vertices, it is very difficult to draw two edges between two pair of vertices, so that is why to reduce the clutter sometimes we will represent symmetric graphs by means of undirected graphs also. Okay, so that in some textbooks they use that convention. I'll use that also, we'll come to that later. Okay, so that is how you represent symmetric relation. And now we also have studied about transitive relation. Okay, so what is a transitive relation? That is very simple. If A is related to B and if B is related to C, then you should have A should be related to C. Is it clear? So that is how a transitive relation. So let us look at analyze the graph of a transitive relation. Okay, so how is it coming? So you can see that, look at this is a basically graph of a transitive relation. Now 5 is related to 4. Okay, 5 is related to 4. I can see the edge going here. Now 4 is related to 3. You can see the edge going here. So what should happen? 5 should also be related to 3. That is why this edge is coming here. Okay, so you can see that there is a triangular shaped subgraph coming here. You can see that. Okay, look at the direction also important. Okay, look at the directions. Okay, similarly, can you recognize some other things also here, some other type of edges also here? You can see that maybe yeah, 8 is related to 7. You can see that. Okay, 8 is related to 7. Look, 8 is related to 7 here. Okay, now 7 is related to 4, therefore 8 should be related to 4. So that is also, so there's a edge between 8 and 4. So here also you can see the triangle shaped region here. Okay, similarly you can see okay, so, okay, there are also other scenes also there. Okay, can you recognize some others also? Okay, 8 is related to 5, 5 is related to 8 is related to 5. You can observe that 5 is related to 4, therefore 8 was related to 4. Okay, so you can also try to look at this graph and try to recognize other relations also. This is an example of a transitive relation, and you can see that in the transitive relation there are many triangular subgraphs. Okay, because of this because of this relation there are many triangular subgraphs, because if A is related to B, B is related to C, then A should be related to C. So you can see a triangle between A, B and C. Okay, so please look at this graph and try to find some relations between these corresponding vertices. Okay, so I hope it is clear what do you mean by reflexive relation, symmetric relation, transitive relation, and how to represent these type of relations using diagrams. Okay, an example of a transitive relation is basically a congruence relation is transitive. You know the congruence relation we studied earlier. So if A is congruent to B modulo some C some M, and B is congruent to some C modulo M, then A will be congruent to C modulo M. I hope you know what it means by congruence. What is congruence? If A is congruent to B mod M, it means that M divides A minus B, and we have done so many problems related to that in our discrete mathematics course. Okay, so that is so this is also a transitive relation. Okay, so we have studied examples of reflexive relations, symmetric relations, transitive relation, etc. Now let us see what is an equivalence relation. Already we have studied about equivalence relation. What was an equivalence relation? An equivalence relation is basically it is reflexive, symmetric, and transitive. Okay, so for example, parallel to is a reflexive relation. Okay, parallel to is a reflexive relation. Okay, then what was other equations? Congruence is an equal congruence. Okay, congruence is basically a reflexive. Congruence is basically an equivalence relation. Okay, equality is an equivalence relation. So we have studied many examples of equivalence relations in earlier classes, and now let us look. Here we are basically not interested in equivalence relation. We are interested in the graphs of equivalence relation. Okay, so here what we have drawn here is actually we have drawn the graph of the congruent modulo 3 relation on the numbers 10 to 20. Okay, so here actually we have drawn the congruent modulo 3 relation on the numbers 10 to 20. Okay, so this is how the graph will come. Okay, so you can see the graph, you can see that it is reflexive, that is why every vertex have nodes are there, self loops are there, every vertex have self loops. Okay, and you can see triangles there, and I have represented the symmetric uh, property using undirected line segments. Otherwise I should have drawn 10 to 13, then 13 to 20, so this graph would become bulky. That is why we have resorted to basically undirected line segments, undirected edges for symmetric, so for showing symmetric relation. This just means that you can go from 10 to 13, and also you can come back from 13 to 10. So this is actually the graph of this relation on the set of elements from 10 to 20. Okay, so if you look at this graph, what can you say? Basically you can see that this graph is disconnected. Okay, or you can say that these vertices are grouped into three distinct components. Okay, three distinct components or three distinct classes. Okay, so that no vertex is common between these two classes, these three classes. So you may have studied that in an equivalence relation the elements could be partitioned. Okay, you have studied this in that. So partitioned into equivalence classes. Okay, so only those elements of the equivalence classes would be related. So if this is an equivalence relation, you can actually partition it into distinct equivalence classes. Okay, and such that in those classes the elements would be related. For example, if A is lying there, C is lying, A would be related to C. Suppose D is lying here, so A will not be related to D, C will not be related to D, but A would be related to C. So A and C are in one class, and D would be in another class. So similarly, if you draw the graph of a equivalence relation, you will be getting a disconnected graph depending upon the number of equivalence classes. So in this problem there were three equivalence classes because of here we are using modulo 3. So three equivalence classes, so modulo means you are getting the remainder. So when you divide by 3, the possible remainders are 0, 1, 2. So depending upon that, so there will be an equivalence class corresponding to 0 here, that is here, this one. There will be an equivalence class corresponding to 1 here, that is this one, and there will be an equivalence class corresponding to here, so that is this figure. So when you draw the graph of an equivalence relation, you will be getting disconnected component, you will be getting components. Okay, and they will be corresponding to the equivalence classes also. So this is how the graph of an equivalence relation would look like. Okay, so that is a thing also here. So this graph is symmetric, it is reflexive, and it is transitive, and it is also disconnected. Okay, because of the equivalence classes. Now let us look at some common remarks that you can see that every binary relation can now be represented by a digraph without a parallel edges. Okay, why is it so? Because what do you mean by parallel edges here? So suppose this is a digraph. Okay, suppose this is a digraph like this. Okay, so suppose this is 1, 2, 3, 4, and parallel edges means again suppose I am drawing an edge from 1 to 2. Okay, so when you represent binary relations, there will not be parallel edges. Why? Because already if there is 1 related to, there is no meaning saying that again 1 is related to 2. So already there will be only one element of the form 1 2 in that relation. Okay, there will not be two elements of the form 1 2, so there will be no parallel edges. So parallel edges is coming when the n vertices, when the initial vertex and the terminal vertex are just the same. When you write the binary relation, you will not repeatedly write 1 is related to 2 again and again. Okay, you will only write it once. So when you have a graph without parallel edges, it represents a binary relation. Okay, so if you have basically if you have a directed graph also, you can write a binary relation from that directed graph also. Suppose you are given a directed graph, how will you write a binary relation? You can easily write it down by just noting down the corresponding relation. So if you look at this graph, the corresponding binary relation would be 1 2. okay, then 3 2, okay, then there is 3 4 is there, then 1 4 is there. So when you have a graph, you can write down a binary relation. Now in the conversely, if you have a binary relation, you can write a directed graph. So this is how there is an equivalence between this binary relations and also this directed graph. And remember, in those type of graphs, there will not be parallel edges because we don't repeatedly write the same relation. Okay, that is why there is no parallel edges. Okay, and similarly, there are other ways to represent relations also. Okay, you can also represent relations using matrices. So that will be called relation matrix, and we will study about how matrix representation of graphs in the coming modules. So when you come to study that, you can see that the graphical representation of a binary relation and the graphical representation of a digraph would be just the same. Okay, when we study adjacency matrix, we will come to see that. So when we study the matrices, we will study more about that. So there is also an equivalence in the matrix sphere also. So we will study how to represent a digraph using using a matrix. It will be called adjacency matrix. There is also an incident matrix. So we'll study it later. So when you represent it like that, you can also always see that it will actually be the same as the matrix corresponding to the binary relation. Okay, and moving forward, this is a question problem here, homework here. Can you please try to write down the relations here. Okay, so this is your set B, and a relation is being defined on a set here B here. So the relation is A and B are related if 2 is divides A plus B. Okay, so first of all, you have to write down which all elements will come in that relation. Okay, once you write that, try to draw the diagram. For example, I can give you one element. For example, here 2 and 4 are related because 2 plus 4 is divisible by 2. So I will write 2 4. Again 4 2 also will be related due to symmetricity, and similarly 5 and 7 are related, 7 and 5 will be related. So draw it like that. So write down all the relations possible and then draw the vertices. Your vertices would be 2 4 5 7 8 9. Now 2 and 4 are related, so like this it will be coming. Similarly 5 and 7 are related, you can draw it like this. So try again, 2 and 2 is again related, 5 and 5 is related, so there will be nodes also. So there will be self loops also, so try to draw that. Okay, so this is how we represent binary relations using these matrices. Okay, and moving forward, we'll come to an interesting geometric concept. We'll be extending our concept of walk and also the path to these problems. So we'll be extending the concept of walk and circuits to directed graphs also. Okay, so there are many concepts here. Very simple concepts are here. So what do you mean by directed walk? Let us look at this figure here. Let us look at this graph here. So suppose I am going to write a walk here. Okay, so if I write a walk here, suppose maybe V5 is going through E8 to reach V3. So I started from V5, I am going through E8 to reach V3. Okay, then okay, so V5, I started from E8, I reached it. So this is actually a walk from V5 to V3. It's a very small walk. It's basically a walk from V5 to V3. Okay, and it is a directed walk. Okay, it is going as per the directions of the edges. So this is a directed walk from V5 to E3. So basically, what is a directed walk? It's a walk which starts from two vertices Vi and Vj. Okay, such that all the edges in between these vertex will have the starting point as the vertex before it and the ending vertex as the vertex after it. So that means basically if I write a long walk here, suppose I can write a long walk here. So I will write it. Yeah. So let us look at this walk. So suppose I am starting from V3. Okay. So I'll explain it once again. I am starting from V3. I am going through E6. I reached V4. Okay. I went through E6. I reached V4. Then I went through E3. Okay. I went through E3. I reached V1. I went through E4. I reached V2. So this was my path. So I went through this way according to the direction of the edges. Okay, so I started from V3. I went through E6, I reached V4, I went through E3, I reached V1, I reached V2. Okay, so this is an example of a directed walk. Okay, so what is a directed walk? It's basically a walk between two vertices Vi and Vj, which consists of alternating sequence of edges and vertices, such that each edge has the initial point as the vertex preceding it and the terminal point as the vertex succeeding it. So that's, you can write in your own words. So basically a directed was an alternating sequence of vertices and edges, beginning and ending with vertices. Okay, and such that each edge is starting has the terminal point as the initial point as the vertex before it, and the ending point or terminal point as the vertex after it. Okay, so such a walk is called a directed walk. Okay, so let us look at the definition here. So I have written it here. It's an alternate sequence of vertices and edges beginning and ending with vj such that each edge is oriented from the vertex preceding it to the vertex following it. Okay, so that is the meaning of a directed walk. Now that is, there is also another concept called a semi walk. Okay, so what do we mean by a semi walk? Okay, so semi walk is nothing but the walk in the traditional sense. Here we are not concerned about the direction. Okay, so it has actually no use in the case of directed graphs, but still let us try to understand what is a semi walk. Okay, so what is a semi walk? For example, I'll give you a semi walk. For example, if I start from V3, I am going through E1, V1, E4, V2. Okay, so I start from V3, I am going against the direction. Okay, so I am not interested in the direction. So actually the edge is from V1 to V3, but I am not interested in that. I am going against the direction. So if I start from V3, I went through V1, I reached V1, went through E4, I reached V2. Okay, so this is not a direct walk because we are not following the direction, but this is against the direction. So what we will say is that a semi walk is nothing but a walk in the undirected graph, a walk in the corresponding undirected graph, which is not a directed walk. Okay, so basically a semi, so if you take the corresponding undirected walk, undirected graph, there will be no orientation or no direction for the edges. Okay, so when you take that undirected graph, this walk will actually, this will be actually walk there. So basically a semi walk is not a directed walk, but a walk in the corresponding the undirected graph. So such a such a walks are called semi graphs. So when you see these semi terms called a semi, it means that it is not a corresponding walk or circuit etc. in the corresponding directed graph, but it will be a walk in the corresponding undirected graph. So because it is not concerned about direction, it is going against the traditional notions of direction there. Okay, so I'll give you another example of a semi walk here. You can, so if you see that here, so there is one other example they have given here. Let us look at that. So if I start from V5, I went through E7. So if I start from V5, I went through E7, I reached V4. Again I went through E6, I am going against the direction. Okay, I went through E6 to reach V3. Okay, then once I reach V3, again I am going through E1 to reach V1. So we are not following the direction, so it is not a directed path, but it is actually a path in the, what you say, in the corresponding undirected graph. Okay, so that is what is meant by semi walk. Okay, so sorry, here it is, here I have to write semi walk here. So semi walk. Okay, so direct walk or direct path. Okay, so it's okay. Yes, the meaning is understood. Okay, so I hope you understand what do you mean by directed walk, directed path. So directed path is a path in which there will be no vertices which will be repeated. Okay, and similarly you can also define what do you mean by directed circuit, semi circuit. Okay, so a circuit, I hope you know what a circuit. A circuit is a closed walk which does not contain repeated edges. So a directed circuit is actually a closed walk which does not contain any repeated vertices and which follows the direction, that is called a directed circuit. Okay, so if you see a directed circuit, I can give you an example of directed circuit here. So if you look at this graph again, if you come to this graph, can you give me an example of directed circuit here? Okay, if you look at these edges, look at these edges, look this, I'm starting from E1, you are going through E1, you're coming back at E6, and then you go back to E3. So this is actually a circuit now with no repeated edges. So you start from V1, went through E1, you reached V3, you came back through E6 to V4, then you went through this E3 to V1. So this is actually following the direction and you are getting a circuit. So this will be a directed circuit. Okay, now can you give me an example of a semi circuit which does not follow or obey the direction? It's the same one you can take. You start from V1, you go through E1, you come through, maybe we come through V3, you reach E6, and you take this edge E2 there, so that you violate the direction. Okay, so if you go through E1, E6 and E2, this is going against the direction. So this will be actually not a direct circuit, it will be a semi circuit because it is a circuit in the corresponding undirected graph. So I hope it is clear what do you mean by a directed circuit and also a semi circuit. Okay, and moving forward, let us also discuss some new concepts here, very simple concepts here. Okay, what do you mean by strongly connected? So we actually, I hope you know what's a connected graph. Okay, so a graph is said to be connected if there is a path between any two pair of vertices. Okay, so a graph is said to be connected if there is a path between any two pair of vertices. So that is what we have studied in our usual graphs. Okay, so in a directed graph, so there are two types of connectedness. So, okay, so there are two types of connectedness because we have studied about two types of paths here. We have studied about directed path and also semi path. Okay, a path which follows the direction and a path which does not follow the direction. Okay, a graph is said to be strongly connected. So if it actually follows, it actually follows the direction. That's the main idea. Okay, so a graph is said to be strongly, a digraph is said to be strongly connected, but if between any two vertices you can always find a direct path. Okay, a graph, very simple idea. If a graph is said to be strongly connected, if there is, if there between any two vertices you can always find a direct path, then that graph is said to be strongly connected. Okay, for example, if you look at this graph, okay, you can actually find a path from 1 to 2. So where is it? You start from 1, you can reach 2. Can you find a path from 2 to 1? That is also possible. You can start from 2, go to 3, you can come back at 1. So this is an example of a strongly connected graph. Because if you take any two vertices, you can always find a directed path. Okay, so if you start from 4, I can reach 2. How will I reach 2? I'll start from 4, go to 3, you will reach 1, come to 2. So between any two pair of vertices, you can always find a direct path here. So can you find a path from 2 to 4? That is also possible. Start from 2, go to 3, reach 1, come back at 4. Okay, so this is the meaning of a strongly connected digraph. Okay, and what is a weakly connected digraph? A weakly connected digraph is basically, first of all, it's a connected digraph, but it will not have a direct path from every vertex to every other vertex. Okay, so you cannot find a direct path from any between any two pair of vertices. You cannot find a direct path between every pair of vertices, but actually it will be connected in the usual sense. So we will say that a digraph which is not strongly connected, but whose undirect graph is connected, is called a weakly connected digraph. So these definitions are very important. They can ask you the definition and also the corresponding examples also. Okay, so define a strongly connected digraph with examples, define a weakly connected digraph with examples. So these are some examples of weakly connected. So let us see one example of a weakly connected digraph. So if you look at this graph, you can see that this is a connected graph. Okay, but it is weakly connected. Why? Because if you look at 1, you can't go from 1 to 3. Okay, so there is an edge from 3 to 1, but there is no edge from 1 to 3, or there is no path from 1 to 3. You cannot reach 3 from 1. Okay, so this graph is not strongly connected because there is no directed path between any two pair of vertices here. Okay, there is no directed graph between any two pair of vertices here, but this graph is actually connected in the traditional. This graph is actually connected in the traditional sense. So I hope it is clear what do we mean by a strongly connected digraph and also a weakly connected digraph. Okay, so I hope it is clear. A weakly connected digraph is basically a connected graph, but it will not have a direct path between any two pair of vertices. Okay, so these are examples. So remember some examples for examination. Okay, so and again, so when you are saying that a directed graph is connected, it can mean two things. It can either be a strongly connected digraph or it can be a weakly connected digraph. Anyway, the undirected graph would be connected. Okay, and now if the graph is disconnected, it means that if it is not connected, it means the graph is called that graph will be called a disconnected graph. Okay, so if you say that a digraph is connected, it can be strongly connected or weakly connected also, but anyway the digraph would be actually connected. Okay, anyway the underlying graph would be actually connected, so it can be this one or this one. So what do we mean by disconnected digraph? Means actually it will not be, the undirected graph will also be not connected. So that means there will be some components there. Okay, so I hope it is clear what is a disconnected graph. A disconnected digraph is basically a digraph which is not strongly connected and also not weakly connected also. Okay, so that means the underlying undirected graph will also not be connected. That means there will be many components like this, so it will be divided into several components. So that's the meaning of a disconnected graph. Okay, and now there is one more terminology here. We will say that a vertex B is, so suppose we will say that the vertex 3 or vertex 3 is reachable or accessible from 1 if there is a directed path from 1 to 3. Okay, so we can say that, so in this graph every vertex is reachable from every other vertex, but if you look at this graph you can say that the vertex 2 is reachable from 3. Vertex 2 is reachable from 3 because I can reach 2 from 3. So if I start from 3, I can find a directed path which starts from 3 and ends at 2. Okay, so that is what you mean by a vertex is reachable from another vertex. Okay, so if I start from 3, I can reach 2. But I can say that 3 is not reachable from 2. Why? There is no directed path from 2 to 3. Okay, so 3 is not reachable from 2, but 2 is actually reachable or accessible from 3. So I hope it is clear. If there is a directed path, we'll say that it is reachable or accessible also. Okay, so there can also think of another thing. In a strongly connected graph, every vertex is reachable or accessible from every other vertex. That's the definition, because between any two pair of vertices there is always a directed path. So a strongly connected graph is always reachable or accessible from in every other vertex. Okay, but in a weak other types of graphs it is not be reachable. Okay, so that is some terminology which we have discussed here. So I hope it is clear, and let us come to the final section here. So since we have already talked about two types of connectedness, we can also now talk of disconnectedness. So suppose I am talking a disconnected graph here. Okay, so let us take a disconnected graph here. Okay, so suppose I have a disconnected, so look at this graph. This is a disconnected graph here. It has two components are there. Okay, and if we look at these two components, so what is a component actually? What do you mean by component? A component is actually a maximal connected subset of the graph. Okay, a component is actually, when you're talking about the usual graphs without reference to the direction, a component is actually the maximal connected subset. Okay, for example, the G1 is the maximal connected subset and G2. So here actually if you look at this graph, this G1, this is the maximal connected subgraph of the given graph G, and this is another maximal connected subgraph of the given graph G, because we cannot make it any bigger. So a component is actually a maximal connected subgraph of the given graph. Okay, so this we know from earlier sessions. Okay, now we have studied two types of connectedness. Now what is it? It was strongly connected and also weakly connected. We have studied both these concepts. So a component need not be strongly connected. You can see this. A component need not be strongly connected. So if you look at G2, if you see this vertex, there is no directed path from this vertex to, there is no direct path from this vertex to any other vertex, because you can't go start from here to reach this vertex. So this is not strongly connected. Okay, so a component need not be strongly connected. It is obviously weakly connected, because the underlying graph is actually connected. So a component need not be strongly connected. So that you have to first of all understand. So if you look at this component also, this is not strongly connected. What do you mean by strongly connected graph? That means any two vertex, between any two vertex there should be a directed path. So if I name this vertex as 1 and if I name this vertex as 2, there is no directed path from 1 to 2. There is a directed path from 2 to 1, but there is no directed path from 1 to 2. If I name this vertex as 3, I cannot find a directed path from 1 to 3 also. So this graph is not actually, this component is not strongly connected. The same applies here also. Suppose this is actually a vertex A, this is a vertex B. There is no direct path from A to B. Okay, so that is mean by the components need not be strongly connected. Okay, so now we will look, if you look closely at the components you can actually find some, you may sometimes you may find some strongly connected portions of the component. You can find sometimes some strongly connected portions which are there in the corresponding components. So because if you look at this graph G2 here, if I just consider only this portion, I am just considering this portion here. Okay, I'm just consider, suppose this is the edge1, this is vertex 1, 2, 3. If I just consider only that portion, you can see that that portion is actually strongly connected, because I can go from 1 to 2, I can come from 2 to 1. How will I go from 2 to 1? I can go from 2 to 3, then I will reach 1. And similarly, I can go from 3 to 1 and also 1 to 3 also. How will I reach 1, 3? I can go from 1 to 2 and then come to 3. So this component can contain strongly connected portions. So such maximal strongly connected portions are called fragments. Okay, so what are fragments? So this is also important. They can ask you what do you mean by fragments. What are fragments? Fragments are actually the maximal, that means that's the maximum possible. Okay, the maximal strongly connected subgraphs of components. Maximal strongly connected subgraphs of components are called fragments. So here you can find a fragment here. Okay, so the fragment here is made up of the edges E11, E13 and E12. Okay, so can you find some fragments in this graph G2, G1? Can you look at this graph and find some fragments here? Can you find some fragments here? Look at this. Can you look at some fragments here? Okay, so if you look at here, you can see that, so there can be many fragments. Okay, so if you look at this one, maybe E2 and E1. Okay, so E2 and E1. Look, if you look at this, but suppose I'm naming it as simply 1 and 2. I can go from 1 to 2. I can come back to 1 to 2. So this is if this can be a fragment. I don't know it's a fragment. If it is fragment, it should be maximal also. So what will happen if I include this edge E3? So if I include this edge E3, suppose this is vertex 3, this is the vertex 4. Okay, suppose it is like this. Now, will 1, 2, 3, 4 form a fragment? Why? So if there is a 1, if I start from 1, I can go to 3, but if I need to come back, can I move from 3 to 1 here? If I need to go from 3 to 1, I should take this path. So I should go from 3 to E5 to reach 4, but now I can't come back to 1. So 3 cannot be part of a fragment in which 1 is lying. And similarly, 4 can also not be part of a fragment in which 2 is lying. So the maximum possible one is only this one, which contains 1 and 2, or that means one fragment is actually E1 and E2. So this is one fragment in the first graph. Okay, if you see that 3 cannot be they're lying in the fragment in which 1 is lying because I can't go from 3 to 1. Okay, so can look for some other fragments here. So similarly, if you look at this one, if I just name this vertex as, suppose I'm going to name this vertex as maybe A, B. Can A and B lie in the same fragment? No. Why? Because there is a path from A to B, but there is no path from B to A. So A and B cannot lie in the same fragment, but B alone consists of a fragment because there is an edge from which starts from B and ends at B. So I can start from B and end at B. So this alone will constitute another fragment. I'll just call it as just E10. So this E10 is another fragment. Okay. Now can you think of some other fragments also? Can there be some other fragments here? Okay. Can you just think of, suppose this is A, this is C, this is D. Okay. So I can go from C to A. Can I go from A to C? Of course, I can start from A, I can reach D, I can reach C. Okay, and similarly, can I go from C to D? Again, I can go through this to reach D. So basically, this also will constitute a fragment. Okay, so what is it? So the edges here, if you look at that one, edges E5, E6, E7, and E8. E5, E6, E7, and E8 will constitute another fragment. Okay, so in this graph, you look at this graph. I hope it is clear. What is a fragment? The component need not be strongly connected, but it will have some subgraphs which are strongly connected. We are just picking it up. So the strongly connected maximal subgraphs of a component are called the fragments. So in this corresponding graph, we have written some fragments. So let us write it once again. I am just writing the edges only. So we have written some fragments. One was your E1, E2. This was one fragment. Another was maybe E10 alone constituted a fragment. Again, there was E5 was there, E7, E6, E8. So this constitutes of another fragment, and this one there was E11, E12, E3. So in the next component there was E11, E12, E13. Okay, so these were fragments. So it doesn't mean that every edge should be there in a fragment, because E3 cannot be there in any fragment. Okay, so we have seen that E3 cannot be there in any fragment because the vertex corresponding to E5 has a problem that once you reach that vertex, you cannot go to this vertex using this E3. Okay, so if E3 is part of a fragment, this vertex, the first vertex, suppose this vertex is named some X, this X and C should lie in the same fragment. Okay, so if E3 is part of a fragment, this X and C will be lying in that fragment, but you can come from X to C, but you can't go from C to X. So E3 cannot lie in any fragment. Similarly, E4 also cannot lie in any fragment, E9 also cannot lie in any fragment, using the same logic here. And using the same logic, E14 also cannot lie in any fragment because these two will not lie in the same fragment. Okay, so E14 also cannot lie in. So it doesn't mean that all the edges should be there in the fragment. We are just writing out the maximum possible strongly connected subgraphs here. Okay, so I hope it is clear what you will mean by these fragments. Now, if you look closely now, if you have understood all these concepts, I know that it's very difficult. We have discussed so many concepts here. Okay, now we'll come to a final topic also. So with that, this directed graph and the second module is over. Okay, so if you look at these fragments, so these fragments are actually very closely connected, very strongly connected. You can move from one vertex to other, you can come back at this vertex again. Okay, so actually they are very strongly connected, they have a strong bond. Now if you fuse all these vertices into one, okay, because they are strongly connected, I can start from one, I can go, suppose this is my vertex V1, okay, V1 and V2. Okay, this is, suppose I am naming at v3, v4, v5, v6. Okay, so this actually, these v1 and v2 are very strongly connected. I can start from v1, I can reach v2, I can start from v2, I can reach v1. So they are very strongly connected, so they are very much bonded. So if I replace them by a single vertex, okay, so I'll going to replace a fragment by a single vertex now. Similarly, this one, look at these three vertices, they are also part of a fragment, they are very strongly connected. So that means I can start from v3, I can go to v4, then I can come to v6, I can go to v3. So I can interchange between all these vertices because they are very strongly connected. So now what I'm going to do is that I am going to replace all the corresponding fragments by a single vertex. For example, I'll just replace v1 and v2 by a single vertex like this. Okay, so this vertex represents now v1, v2. Okay, the next fragment is consisting of v3, v4. So I'll represent this vertex by v3, v4, v6 will now be represented by a single vertex because they are very much strongly connected. So they are very much bonded. So I am just collating, or I am just reducing that three vertices into a single one. So I'm just reducing the fragment into a, representing the fragment into a single vertex to make the graph more compact. Okay, so this will help to simplify a very complex graph into a simple vertex, because when if you reach v1, there is always a way to reach v2. So in order to study all the properties of the graph, in order to study a big graph, we can actually reduce the fragments, because if you have a fragment, you can always find path between vertices in a fragment. So in order to study overall properties of the graph, what I am going to do is that if you want to find a path in the overall graph, what I am going to do is that I'll first of all reduce the fragments into smaller vertices. Okay, then I'll find a path between correspond different fragments now. So once you find a path between different fragments, it is always possible to find a path between any vertices also. So when you can reduce bigger problems of path finding problems into smaller ones by just collating the fragments into a single one. Okay, suppose v1, v2 is a fragment. Okay, now I'll just represent this v1 and v2 by a single vertex. Similarly, v3, v4, v6 is a fragment. I am going to represent by a single vertex. Now all the, and similarly, this E10 just consists of one fragment. I'll just represent by just v5 here. Okay, now all the fragments have been represented, and I know that there is a edge from, there are two edges from the first fragment to the second fragment. There are two edges are there. Now those will be represented by a single edge. Okay, this will be represented by a single edge, and I'll write it here for information that E3, E4. Okay, so these will be represented by a single edge there, and similarly between this fragment and this fragment there was an edge there. Only one edge is there. I'll just represent by this edge E9. Okay, so this representation, okay, this representation in which the fragments have been reduced to a single vertex is called condensation of the graph. This is called the condensation of the graph. So this is also called condensation of the graph. If you understood this, let us look at the condensation of this subgraph also. Okay, so here the fragments of, suppose this we have used till v5, so v6 also, v1, v2, v6. Okay, suppose this is v7, v8, v9 and v10. Okay, how will you write the condensation of this graph? This is actually the fragment here. Okay, so I'll represent that by just one vertex which represents v7, v8, v9. Okay, v7, v8, v9 and v10 by one vertex, and there is an edge from v7, v8, 9 and to this one, that is nothing but e14. So this representation is called the condensation. Now you can see that this bigger graph, this very complex graph is now being reduced to a much more simpler graph. Now it is very easy to study path finding problems and etc. in this type of graph. To check the properties, it is very easy to study it in this graph. So this is called the condensation of the graph. Okay, usually in the condensation we'll write the number of, we write instead of the vertices and the edges, so I'll write in that format itself. So the first fragment was represented by the edges E1 and E2. Okay, the second fragment is represented by the edges. What are they? This is represented by the edges E5, okay, E5, E8, okay, E8, E7 and E6, E7 and E6, and the last one is represented by the edge. Okay, instead of V5 I'll just write down the corresponding edge, it is nothing but E10. Okay, so this is usually how you write it. So use the edges so that you have a bigger picture. Okay, so you are actually reducing all the fragments into a single one now. Okay, Okay, so that the bigger graph is now become a simpler graph. So this is called the So here also we'll write it like this. Instead of this one, we'll write it. I write it as E11, E12, and E13. Okay, so there is no edge here. So I'll just write it as vertex like that. Okay, so this is what do you mean by the condensation of graph? That means I hope it is clear what is condensation. For that, you need to understand components of a disconnected graph. Then you have to understand what do you mean by fragment. Fragment is a maximal possible strongly connected subgraph of a component, and now you are reducing these subgraphs into a single vertex. Okay, so and then if there are many edges from one fragment to another, you will represent by a single edge. So that is what is meant by a condensation. So I have given the definition of a condensation here. We can look at the definition. Okay, please look at the definition. Try to draw the condensation once again here. Okay, so this is what you mean by condensation. Okay, so I hope it is clear what you mean condensation. Just go through the definition and try to understand the definition by means of this example. Try to draw a condensation of some other diagrams also. I will also give you some homeworks. Okay, so very simple. Try to find the fragments. You represent the fragments by a single vertex. Okay, if there are many edges going from one fragment to another, represented by a single edge. Okay, it's a very simple thing. So this complex graph is now being reduced into a very simple graph. Okay, this is the meaning of a condensation. Okay, and if the graph is actually strongly connected, its condensation would be just a single vertex only. Why? Because all the given strongly connected graph itself will be a fragment, because you can always reach one vertex from another. So the given vertex itself will be a fragment. Okay, so it can always reduce in a single vertex. So if a graph is strongly connected, its condensation will just be a single vertex. And you can can you think why a condensation of digraph will not have a directed circuit? The condensation of digraph will not have a directed circuit. Just think why. Just tell me tomorrow why it is so. Okay, if it is a directed circuit, if it has a directed circuit, it means that fragment was not the maximal. That's the idea there. Just think about this concept and tell me why the condensation of a digraph has no directed circuit. If you want, you can type it here also. Tell me just why the condensation of a digraph has no directed circuit. Okay, so that's the meaning of this. And also I have just updated one problem also regarding strongly connectedness. You can go through that problem also. So that's it. So we have studied many definitions here. So this is the end of the digraph and also second module. So we'll stop here. Thank you.